Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
As we go, so let me introduce myself first. My name is Wenming Yi, and I am a senior program manager at the Microsoft Research Connections. So I have been working at Microsoft for about 5 years. So I would like to make this session fairly interactive. So if you have any questions, you're very welcome to ask them, and you can ask them in Chinese, and I can, I'll repeat them in English. So there's no problem. There's no problem there. So ask me any question you like. The second thing is that I am actually from Boulder, Colorado. So I went to high school, college, and graduate school there. So this is basically in the middle of the country in the U.S. So what's also interesting about Boulder, Colorado, is that it is the home to a lot of environmental agencies and government agencies there. One of the most notable ones are the ones that I've listed here. So University of Colorado, we have a lot of environmental science and also organizations that are funded within the university. And then there's UNIVAC. So that particular organization is funded by National Science Foundation. And what they do is figuring out the physiques of the planet Earth, and they also collect large amounts of data. The ones that I work with quite a bit is UCAR, University Corp for Atmosphere Research. There's also something called National Center for Atmosphere Research. That's in Boulder, Colorado. So these are the guys that do weather forecasts, and they have quite a few supercomputing centers that they own. There's about 1,000 people there. We actually have a lot of researchers from China that visits them very often. And the other place is called NOAA. It stands for National Oceanic and Atmospherical Agency. And this particular agency also does a lot of weather forecast and studies ocean currents. So a lot of environmental science done there. Then there's the NOAA, we call it NOAA. It stands for National Renewable Energy Lab, and it's about 10 miles or 20 kilometers away from Boulder. What they have is really, really large wind turbines, so they study different types of renewable energy. And then there's Bing Maps. Bing Maps is one of the largest organizations at Microsoft. There's currently, I think, 300 or 400 people there. We're located right in Boulder, Colorado. So what we do there is fly over data, or we use these really, really high resolution cameras. And we put them on a plane, and we go around the world and actually do certain passes and get really, really, really high resolution images. So Bing Maps has in the orders of 160 petabytes of data that they've collected. They spent about 2 or 3 years just flying over the United States, and now they're doing Europe and other places. And there's LASP. LASP stands for Laboratory for Austral Space Physics, and it's part of NASA, and that's actually within the university. So there's a lot of environmental agencies by where I live, so my wife actually used to work for some of these organizations. And this is where a lot of the environmental science is done. I think I missed one, which is NEON. It stands for National Ecology Observatory Network. So they look at the ecologies and they collect huge amounts of data So they also have a lot of collaboration with Europe and also, I believe, China as well. So that's the my brief introduction. And here's the agenda. When I look at the environmental and climate challenges, so some of the things that are becoming really important to our ways of life. And then there's the why cloud computing can actually help to solve these really challenging problems that are getting harder and harder to be able to solve. And I have some common cloud computing scenarios and patterns. So those are the things that architectures that you will be using that are very common in the cloud. So there are certain things that work really well in the cloud. There are other things that is not yet optimal running in the cloud. So I want to help you a little bit to understand a little bit about large-scale compute and also big data in a more practical fashion. And then we have some hands-on materials that you can download. I have a link at the end of the class, which you can download. So we also have a 2-day training class that starts tomorrow. So is any of you guys signed up for that class? Anyone? Oh, you're not? Okay. Well, I have the content here, so I'll go over some of them. So you might be able to use these samples to start working on projects that's relevant to you. So there's also, we have a Windows Azure RFP program where we're giving away huge amounts of Windows Azure hours. I think it's in the orders of half a million core hours equivalent of storage. So it's worth a very significant amount of money. And we are starting to do about 100 of these projects. And from what I've seen is that we have fantastic researchers here in China, and we would love to see some innovation and collaboration with Microsoft Research to really think about interesting ways of using the cloud that no one has done before. So let's go to the next one. So I am I would call an enthusiast of environmental science. So I like environmental science. I work with a lot of environmental scientists. However, I am a computer or CS, computer science major by training. So I do not do science necessarily, but I do I used to work for the Department of Energy as for one of the subcontracting companies. So I do a lot of plasma physics and particle and cell simulations. So very similar to yesterday's keynote. Essentially really, really large amounts of physics data and do parallel simulations on them. So here are some of the issues that we currently see, and everyone sees that. It's all over the headline in newspapers. So I picked up a newspaper, and the headline is air pollution, right? So a lot of these problems are becoming harder and harder to solve. So there's the air pollution, and also there's over-fertilization, there's soil pollution. A lot of these problems are becoming worldwide. So in fact, in California, there's a significant amount of soil pollution because of over-fertilization, and then those fertilizers go into rivers. So it's a problem worldwide, not just necessarily in China. And also there's waste and toxin management, so that includes nuclear waste and other types of waste that are toxic in the landfill, and they get into the groundwater. So there's a lot of things that are happening that we don't yet have the control over. So these are, I think, very big challenges, which I'm hoping that environmental science to take off and we'll be able to fix them. And then there's energy and natural resources. I call them the energy security. Oh, by the way, I call it environmental debt. what that really means is that when we write software, I'm a software person by training. When you write bad software, we call them technical debt, meaning that you are not paying, so you're owing someone the good work, right? So this I call the environmental debt because of all the pollutions and problems that we've created because of the economic growth, right? But it is necessary, for people to get to certain living standards. But on the other hand, pollution is becoming a very large problem. So the second thing is really the energy and natural resources security. So yesterday there was a headline saying that China will become the world's #1 oil importer. So the fact is that China doesn't actually produce a lot of oil itself. It has to import a lot of it. And the rest, it has to make up by coal. So there's 3.7 billion tons of coal being burned every year. So this is actually a dinner conversation that I had with a friend of mine who works for one of the coal agencies in China. I think he regulates the production and one of the regulation agencies for production of coal. So some of the things are fairly interesting. So in the U.S., every year there's about a third amount of coal being burnt, which means there's a significant amount of air pollution if you burn that much coal. So we actually have an example which we can show you. Given the pollutants, meaning if it's SO2 or any type of pollutants, you will be able to figure out what type of source, what the pollution source is coming from. So for example, it could be coming from diesel, it could be coming from burning coal or burning wood. So there's different types of properties when you burn certain type of materials. So, and also there's natural disaster. So earthquake and hurricane. So I lived in Boulder, so we just had a flood. I think it was making national headlines. So what happened was, I lived there for 22, 23 years. It's a very dry place. Suddenly, there was 20 inches of rain all dumped in Boulder at once. So you look down the street, it's ocean. So basically, you couldn't even see the streets. So I think most of the houses are actually flooded in Boulder. There's actually several people that told me that they went to a neighbor to make a phone call, and when they came back, the house is gone, and they just got washed down the street. So natural disaster is a huge risk in that, and how do you do predictions of these problems? So these are the challenges that I see are very important for us. And so how might cloud computing be able to help with these types of problems? One is that, hold on one second. So one of the things is that cloud computing allows you to scale out on demand, meaning that a lot of these really large problems cannot be solved on your desktop computers anymore. So normally you would bring up a workstation, open MATLAB, and run that. But the problems are becoming larger. So there's a lot more data that's being ingested. So you can't really just say, okay, I would like to ship 1 petabyte of data to my laptop, and well, let's analyze that. So all the analysis has to be on centralized server. The other interesting thing is called the always on and reliable. Cloud computing is always on, so I've had machines that are running for 2 or 3 years that I deployed as service, and it has been running there for 2 or 3 years. I haven't ever shut it down. So it's just running there. So anything that happens to the hardware underneath, anything bad happens, all of that is taken care of for you. So it will be moved to good hardware if something happens to the hardware. So we have some demos of that and how that works. Another interesting thing is the abstraction for hardware and IT infrastructure. So for example, I have a service that's running in the cloud right now. Has been about 2 years, and I don't really know what hardware they have changed. It's significantly faster now. But I don't have to worry about that because, so normally when you run a program, you have to shut down the server, install the operating system, get it on, onto the network again, reinstall your software, it may be a different version. So all of that is essentially taken care of for you with an abstraction. So if you think that cloud is expensive or cloud is slow at the moment, 6 months down the road, it will be twice as fast and twice as cheap. So there's a significant amount of resources being devoted to cloud computing. So there's also a lot of competition. So it's going to become cheaper and more economical than building your own servers. And also centralized compute and data storage. So for a university, probably have really fast network. For companies, maybe, right? But in the cloud, we have some of the best networking, and many also, many other commercial vendors also have that too. What that really means is that you will be able to connect at hundreds of times faster, and it's always going to be running there, right? And convenience and collaboration is also important. You can share data, and you can run live simulations, and you can share these instances on the cloud so that others can run your simulations. So let's go there. So this is actually one of the very, very, it's like a one-core machine. So one of the smallest machine. And this morning I just ran this. So in my hotel I get maybe 1 megabps. I think it got to maybe 3. That's as fast as it goes. And then you look at that running on a 1 core. So if you run on 8 cores, it actually double or triple the amount of speed. So it would actually go to almost 10 times as much speed if you have a machine with a lot more cores. So here this is going at 100 times faster than anything you have. So that's why you really need cloud computing because it's always going to be there and it's going to be reliable, right? So it works very well for streaming type of applications. So for example, if you have Internet of Things or smart building sensors that are streaming data in, you would not want to have a server sitting in your house, probably not. So you really want something along the lines of maybe a little server in the cloud that streams the data and do some of the processing there. Okay, so here are some of the common cloud computing pattern scenarios and patterns. So this is just from my personal experience from working with customers. So I work with both commercial customers as well as customers that are in the science and research community. So here are some of the common patterns. One is the workstation in the cloud. So for example, if you just wanted to take something that runs on your desktop and you want to put it on the cloud, it works perfectly fine. So you just run remote terminal service and you go into the cloud and you can run MATLAB, you can run R, you can run pretty much anything you want. So you can go on that machine and install anything you want. Turn it off, you're not paying for it once you turn it off. And when you're using it again, turn it on. So that's one of the scenarios. And the second one is the always on cloud service, meaning that once you deploy a cloud service, it could be a website plus some compute in the back end, it's always going to be running because we guarantee certain levels of SLA or service level agreement. So we'll say, okay, it's going to be 99.95. So for every year, it will be down only 4 hours, or you get some of your money back, right? So that's the kind of things that you can't really do yourself. And even some of the companies, they cannot do that themselves. And here's some other scenarios. There's some HPC. So how many of you actually do HPC, or high performance computing, MPI applications? Not very many, right? Okay. So HPC, what that does, it does numerical modeling. So you usually have these nonlinear, linear solvers that you have to run, right? using MPI. So there's a lot of communication between different machines in a cluster. So that doesn't generally work very well in any of the public clouds, but we are going to be having very fast interconnect, so 40 gigabps per second interconnect with low latency. So those hardware are going to be in the cloud in the near future. The second thing is that clustered parametric sweep, meaning that you run a program 100 times. So you can run it, so I have a weather simulation here which does a weather forecast. I can run it on 100 cities, right? So because each of these units of work is independent of each other, right? So that's how that works. And it works very well because in a cloud you can pretty much scale out to as many machines as you like, if that your account allows it. And then there's the big data processing. So in big data, I've divided it up into 3 categories. One is batch processing. So meaning that you're using the hard drive on each of the computers to do the processing. And it can process a huge amount of data. So essentially Hadoop is called batch processing. And then the second one is interactive type of compute. So that would be something called Hive or Shark. What that means is that you can run SQL-like queries against really large amounts of data. And it will be turning that into a MapReduce call. So underlying, it will be turning it into a MapReduce call. And then there's the real-time processing. So for example, if you have a lot of sensors that are streaming data in, so this would be a great way of doing things. So there are tools that can do these for you. So I have a demo here, which I wanted to show you guys. I actually have it running live. So what it's called is Weather Research and Forecast is a cloud service. So every day you watch the weather service on your TV, and how do they know that in 3 days it's going to rain or not? So they have a finite difference model. Essentially, they have data points that they've collected at a certain point, and then they run a finite difference model to do the prediction. So this code is really old. It's probably 15 years old, and it's called WRF. Probably some of you have heard of it. So what this does is it does a solve on really large matrices, and then what you do is we can take that result and plot it on big maps. So one of the things is that I can run 100 cities or hundreds of cities on a single node. So essentially, I'm running these simulations on 8 cores. It takes about 8 hours. So the service I have been running here, it has not died after about 2 years. So people have run about 2,000 simulations on here, and each of them are about 8 hours. So that's a lot of simulations. And I also have a lot of data that my simulation produces. I have 13 million objects that are sitting in the blob storage. So that's a lot of data. And I would normally not be able to store that data. So it just automatically scales that for you. I also have something called platform as a service. So the rule of thumb, if you want to scale, if you don't want to manage your machines, you want to keep everything stateless. So stateless means you don't install any software on your machine afterwards. So you don't keep any states. So anything that you did, it's going to get lost afterwards. So what you do is you can automate that process and create thousands and thousands of machines that just does one thing, or does a certain amount of things. But you're not going to be keeping hard drives with these machines. So anything that happens to that machine, it will just get rebooted, and it will be installed. It will be installing software that you asked it to initially, and it will keep that particular state, right? So, for example, if I have a machine that I have MATLAB that I want to run, right? So in the beginning, when I provision it, when I start this machine, it will install MATLAB, and if something happens to that machine, let's just say the hardware is broken, all it will do is to deploy it onto another machine, and it will be exactly where it was. So it will install the same amount of software on that machine. So the nice thing about it is that you don't have to keep hard drives around. to attach to them, right? Let's look at this particular demo. So the first thing is that it does a forecast. So you can also look at the website. It's called weatherservice.cloudapp.net. So it's actually being running live, so I can actually go there and show it to you. So let's go through these slides first. First of all, it has run about 2,000 simulations so far. And what it can do is it can run a forecast on one city, 180 kilometer by 180 kilometer. It will take you about 7 hours, and then it will do a forecast for 3 days, and you can do up to about 8 days. So the more days you predict, it's going to be less accurate. So I just put down 3 days as a default. So you can just go on that website and do the forecast. And here's how it's done. So this is actually the website. We're going to look at the website after I finish the slides here. So one is that it shows you, it can show you all the forecasts that we have done, and you can zoom in, and then you can see the animation. You can see the animation over Bing Map. And I also have a gallery view, which shows you the snow and temperature data, and it's animated GIF. They're just animated GIFs. So this is the architecture. First of all, when you want to do a weather prediction, you have to have some boundary data. So that boundary data is actually from NOAA. So just as a reminder, NOAA stands for National Oceanic and Atmospheric Research Agency. So I get the data, and then what I do is I keep them in the blob storage. So every 6 hours, this data source actually gets changed. So it's very simple. I just copy the data from the FTP website from NOAA. And the next thing you do is you run the simulation. So you run a simulation against that data set. And it'll take you about 8 hours to do. It's just very compute-intensive work. And then once it's done, and it will take all the information and store them in the blob storage. So we get the data, we do the computation, and we keep the processed data into a blob storage. And then we just show them on a web page, and that's all there is to it. As you can see, it's a pretty simple process. Of course, there's a few more things that happens in between. And this is the Windows Azure portal. You can see that if I start running a job, it will have monitoring that goes to about 90%. And I am running about 100 cores out of 128 cores in this particular account that's available. And you can get up to probably a few thousand cores if you really wanted to. The other interesting thing is that you can look at the instances when you're not running them. You can just scale them back. You can just move a little slider, and it will just use less cores, and that's how it works. So here's the little slider. So right now, if I wanted to do weather forecast for 12 cities, I just move the slider, and that's all I have to do. So what it will do is it will go spin up those machines. It will start those machines, and it will run the forecast for you. And here's also auto-scaling. So what that means is that if my CPU is busy, a few of these machines, it's going to start running the rest of them. So it's going to add more machines if the first few machines are really, really busy. So they're at 100%, it will spin up a few more machines. Here's how it works. So you can see there are 3 types of machines here. One is the head node, which just controls the cluster, right? And then there's the front end, which is the web page that you see. And then there's the compute node, which is 8 cores each. So these are really, really large machines. They have 16 gigabytes of RAM, and they have 8 CPU cores on them. And then you can just move your slider to add more or remove machines as you need to. So this is a screenshot of all the cores that are running. So you can see in this particular instance, we're running at 98% or 99%. I mean, that's a lot of compute-intensive work. So let's just say any of these machines die. I don't have to worry about it because it will get reprovisioned automatically. So it will go to another piece of hardware, and it will redeploy them onto that machine. and then it will just pick up the work afterwards. So the nice thing is that I'm not keeping anything on that machine's hard drive, and I'm storing all the data back into the Blob Storage, which is a centralized storage service. And I can easily copy data 130 megabytes per second. So if I want to copy data into the Blob Storage, into the storage, I can do about 130 if I do it properly. Or it's between 100 meg to, and it's very fast in terms of being able to run that. So if you have a few other machines, you would be able to run it even faster, be able to do it even faster. So for things like Hadoop, it would be to pull data from multiple computers to make it even faster. So let's actually show you a demo. So I have a machine running here. Let's see. Yeah, so I have a machine running here. So this is live, by the way. So if I go to the home page, there's the home page there. I have a gallery view. So the gallery view basically shows you all the simulations that have been done. And I'm going to move it into the window here. There you go. So let me do that again so I can go to my home page. Right, so there's your home page and there's a little gallery. And the URL is weatherservice.cloudapp.net. And I can go to the gallery view. So the gallery view shows you the recent cities that have run the forecast. So I ran one on Lhasa and a few other cities in China. Right? So you can see that that was from yesterday. I can essentially become my own weatherman if I wanted to. Right? So then I can click on one of them and I can animate it at much higher resolution. So let's look at the temperature. So you would probably think that Lhasa would be really cold at night, right? So let's actually animate that a little bit. So it does, actually. It gets to be fairly cold on the outskirts. You can see the color map there, right? So it's a little jumpy because of the internet is not very fast here. But essentially, you will be able to animate a lot of these processes. You can see it actually gets to about maybe even below zero in some of these places. So let me go back. And you can see Guangzhou is really, really hot, right? So you can click on it. Let me see. Can I click on it, please? All right. The network is a little slow. And the other interesting thing is that what you can do is so as I was moving the slider just for the compute instances, I can also move that for the web instances. So the web instances, I can add more. So let me click on the play button here. So it's all JavaScript. This is all Bing Maps, by the way. Yeah, you can see Guangzhou is really, really warm. It's about, 70 degrees. Sorry, this is Fahrenheit. I think it's about 20 degrees or so. So you can see that it shows you certain places are really warm and some other places are a little colder. It's probably because the geolocation of Guangzhou. So there you go. So this is how the system works. And I can also go back and look at the gallery view again. So I can go to gallery. And I can click on things like map. Yeah. Oops. Wait a second here. So what I'm trying to do is try to click on one of these icons where it says timeline, and maps. So I'm having a little bit of trouble pointing to it because I can't see it on my screen here. So let me see if I can click on that a little bit here. It's not quite working. So what it will look like is basically showing you the yeah, there you go. So what it will actually show you is this particular view. It will show you when these simulations are run, so you can browse around the globe and see all these dots and you can click on them. And also you can browse by timeline. Let's just say in the last 5 to 10 hours, I ran 50 simulations. You can see that it ran 50 simulations. So I think the problem is that it's actually because of the, can you guys still hear me? Okay, great. So I'm trying to move this a little bit. We're going to duplicate the screen here. Let me see. So this is IE. So IE works a lot better for this particular demo. So I can go to gallery here again, and I can go to map, and shows you all the simulations that are running. So you can see now, right? So these are all the simulations that people ran. It's not necessarily just people from Microsoft. There's a lot of people that ran simulations. So this is all the ones that ran in the last few months. The other thing you can do is look at the timeline. So here's also a little bit of timeline here. Yeah, it's still taking a little bit of time to load. So you can see the bigger dots are the time where somebody ran a lot of simulations. So today we ran all these simulations for all these cities. But if you click on one of these other days, that there was nobody doing anything, right? So then that day, somebody ran it on 1, 2, 3, 3 cities, and then you can see, this particular day, people ran it on, a few other different places. So it gives you a history of all the simulations that has run on your service. Okay, so that is the demo for running a cloud service. So some of the things to remember is that, one, it's stateless, meaning that I am not keeping anything on the local hard drive. So if I'm moving the slider, it just means I can spin up more instances, right? And the other thing to remember is you can add any combinations of compute resources. So you can add multiple websites, you can add multiple compute nodes. So it's just simply a configuration of a configuration file change. So we went through all this, and let's look at the file copy. We did actually do that. So I have another example here, which it actually ran a few years ago, 2 or 3 years ago. So what this does is it does an analysis of the pollution source, as I mentioned earlier. So for example, if I detect there are certain amounts of pollutants in the air, so I can figure out where they're coming from using something called a non-negative matrix vectorization. It's a fairly standard EPA code. So this is essentially scaled out. You can see that I have a one machine here, interactive shell, I have a little controller, and I have all these little compute engines. This is all done using Python. So you can download IPython notebook somewhere if you on the web if you like. We also have a lot of these things in training, so you can learn about them from the training materials. So here's how it works. One is that you have so essentially here's your PM 2.5. So if you have too much of it, basically it will cause a lot of death. So they actually did the study in Denver. So Denver is a city that it's a valley. So basically it's a valley. So there's a lot of pollution that sits on top of it. So what happens is that when the pollution is really bad, there's people that goes to the hospital. So they want to find a correlation between when the pollution is bad versus how many people actually goes to the hospital that have lung issues. And the second thing is they want to find out is they want to know what pollution source this is coming from. Is it coming from the power plant? Is it coming from too many cars? Is it coming from diesel engine running? Or is it also could also be coming from forest fires? Because Colorado tends to have forest fires, and it will have these smokes deposited, and it makes the air look really bad, right? So there's so essentially it's a matrix vectorization that you can run from the EPA. So here's the the positive matrix factorization, right? So this runs on laptop. This runs on my laptop. So it takes about an hour and a half to be able to run. So taking the same code, I'm using 48 cores. So instead of 2 cores, I use 48 cores on a Azure machine, and I end up having about 40 seconds. So it goes from an hour and 45 minutes on your laptop to about 40 seconds. So you could imagine that I could take these measurements as they're coming in, and I can run these analysis and tell you how much diesel pollution there is, how much is it from forest fires or burning wood, or how much it is from just gasoline engines, right? So these are the things that you can pretty much figure out. It could also be, we also have a oil refinery. So we have an oil refinery that also is being regulated by the EPA. So if the oil refinery is putting out too much pollution, they may shut it down for a while. So this is the way they do this calculation. So basically what we did is simply take this code and parallelize it, right, using Python. And then the runtime goes to about 40 seconds, right? So that's an interesting thing. So the second thing I want to talk about here is NoSQL. NoSQL here. So NoSQL stands for not only SQL, meaning that you're doing unstructured data. So the first property, and actually NoSQL kind of goes with big data, right? So essentially it's non-structured data that's not data that you store in your SQL server. And then it's unstructured data. You can have JSON, right? JSON and CSV. Key value pairs is the big thing about Hadoop. So everything has key value pairs. So you have a key and you have a value. It's pretty simple. But sometimes you might ask me, okay, how do you have a table when you have just key value pairs? Well, that's pretty simple because you can have multiple keys. So let's just say if you want a table, you can have an X and a Y as your key, and then you have a value, right? So essentially that represents a table. In fact, this is how HBase works. So HBase sits on top of Hadoop, and it allows you to have this table structure. The second thing is that you would be able to scale out in the cloud to overcome hardware limitations that you have on premise. So the feature of big data is really to be able to partition them onto many, many machines. So you can have hundreds of machines that have 20 hard drives in them, and you can run them in parallel, so using the disk processing speed to do it. So each machine has, let's just say 20 disks, and you multiply that by 100 megabytes per second. So then you multiply it by 1,000 machines, and suddenly it becomes very fast. Then the other thing is the scale out in the cloud. So the cloud allows you to have multiple machines. You can have thousands of machines without having to purchase them first, right? And then you can turn them off when you're not using it. And the second thing is the commodity, meaning that they're really cheap hardware. They're not, network storage systems that cost millions of dollars. These are just regular machines that you put some hard drives in them. And finally, they have very high throughput, right? So you basically you're using the I/O from multiple machines that have multiple hard drives. So that's the idea of doing big data and NoSQL. So you will be able to utilize many, many machines to work on the same problem. And the reason it scales is because it doesn't have a schema, right? It doesn't have a schema. And it makes it easily dividable into smaller chunks of work that can be worked in parallel, right? Okay, Hadoop is for big data. So how many of you actually used Hadoop, or nobody so far? Okay, how many of you want to use it or think you would be interested? And still nobody? Come on, somebody's got to be interested, right? But anyway, I will let you know. You guys are just being shy here. The first thing is that it's a distributed batch system. So what this does is a lot of these jobs run for a long, long time. And the second thing is it uses MapReduce paradigm, which is really, really simple. Simplicity really scales. meaning that if you want something to be able to scale linearly, you want them to be simple. So MapReduce is a very simple protocol. So it takes huge amounts of work, divide it up onto each of the machines and let them run. So we have some nice little animations. So one of the applications of big data is something called collective intelligence. So suddenly you would have everybody's information all in one place. So in the US we have Facebook, and in the here you guys have what are the social network that's equivalent? I think I heard Run or something like that. So basically you have a place where you have everyone's data. They're all in one place. So you can do a lot of interesting things. So it's, one of the things you can do is collective intelligence. So when you have everyone's data in one place, you can figure out consensus, you can figure out what people are trying to do, or another example is Twitter data, right? Another thing is predictive analysis. So given certain things are happening, what are what's going to happen in the near future given the data that we currently have? So, for example, one of the big data problems that we're trying to solve here at Microsoft is to predict something along the lines of when Windows Azure is going to possibly have a problem, right? So you can fix it ahead of time. So we may look at the data and say, okay, we have the most trouble maybe at 8 o'clock in the morning when this company is running really, really large amounts of data in this data center, right? So if that happens, we could possibly change the parameters of our cloud services to meet that demand. So a lot of that is going to be very useful when it comes to being to have the data in one place. So here's how the Hadoop works. There are two layers. One is the MapReduce layer, and then the second one is the HDFS layer. So HDFS stands for Hadoop Distributed File System. So this is what I was telling you about. Essentially, you have these really commodity hardware, which each of these hardware has lots of hard drives in them, right? And then you can build a file system that's sitting on top of it. But it has to be redundant. What happens when one of the machines dies? So it keeps 3 copies of the same file in one place. And the second thing it does is that when you do a write, it will actually write all of them all at once. So make sure that it guarantees that you have 3 copies at once. So, and it keeps 2 copies on the same network, and it keeps 1 in a remote location on a different rack, right? And then there's the MapReduce function. And MapReduce is pretty straightforward. All you're doing is you are doing scatter and gather, right? So you're taking a large amounts of work and dividing it up to let multiple machines to work on it. And then you collect them back together. So that's how it works. So I call this is the assembly language, the most basic low-level language of MapReduce. Okay, so here's how it works. The first thing is that you take so there's a bunch of data that's distributed onto all these servers, and see, we have a piece of code. So the most important piece, I think, to remember here is that you're moving the code to the compute. So I don't want to move data around because the data resides on each of the machines as they are. And when I want to do some computation, I would take a piece of code and the scheduler automatically figures out where the data is for that particular job. And it will go work on that. So it doesn't have any I/O that happens. So that's what MapReduce is actually working. It's called moving the code to where your data is, right? So the second thing I want to talk about is the something called interactive big data analysis. So what this does is allows you to run scripting language that looks like SQL, the SQL language. So Spark and Shark is actually a Berkeley project. So that came out of Berkeley, and I would encourage you guys to go take a look at that if you're doing large data analysis. One of the things that's really nice about it is that it has in-memory data storage via the resilient distributed data sets. It can be 30 times faster than Hadoop. The reason it can be that much faster is because it caches a lot of intermediate state in memory. So it doesn't do a computation, keep everything to the hard drive, and then read it back in and do the second iteration. So what it does, it keeps a lot of the information in memory, and then there's work to make it redundant. So you're not going to lose any information when one of the machines go die, right? Here's how it works. So MapReduce is very iterative, right? So you do one MapReduce, and then it gets feed into the second step and the third step. So here's the animation. One is that it doesn't write to, well, this is actually the original diagram. When you run MapReduce, it does the computation, writes it on the storage, and then does the second one, and then writes the storage again. But if you use the work in Spark, it will actually cache them in memory, so that it doesn't have to do the I/O. And then it just, that's why it can be about 20, 30 times faster, right? Or sometimes it will say 10 to 100 times faster if it's done properly. And here's something that's interesting. This is something called Hive and Shark. What this does, it allows you to run, this looks like SQL, right? So this looks exactly like SQL. So you don't have to learn how to build MapReduce in Java code, which is really, really long probably. All you have to do is to open a command prompt and run these type of queries on big data. But underlying it has the execution engine that will build an execution plan, and it will still do MapReduce for you. It's just that it can do it much faster. And here's some of the operations that you can do, just giving you an example of them. So these are all standard SQL code, and you can just run them. Of course, it's a subset of SQL, so it doesn't have all the functionalities of it. So there's certain joins that you cannot do. So here's another interesting thing called the RealTime Streaming, stream processing. So this is becoming a very popular topic to talk about. It's related to Internet of Things and essentially sensor data that are coming in. I've actually built an example for you in the training kit, which you can use to start doing your own projects. We'll have a link at the end. The thing is it's developed by and used by Twitter. And the reason you might want to use these software is that it has been tested in these production environment by these really, really large social networks, right? So someone has already built this software and has tested it properly, right? So it's running in production, it's fault tolerant, so you don't want to write your own, probably. And it can scale, so meaning that if you want, there's more tweets coming in or there's more data coming in, if I want to do the processing in real time, it's not a problem. I can simply add more computers to it. So that's very important. It's called horizontal scalability. And it's also fault tolerant, as I just said. There is failover mechanisms in them. So I'm not going to go into too much details of this because we have about 20 minutes left here. The other interesting thing is something called the Kafka, which allows you to do message passing, and I'll go into that later. So Storm is the underlying scale engine. So as you have streams that are coming in, so these are just data that's coming in. So we have these structures that are networked together. One of them is called spouts. So essentially it uses the source of the stream. So for example, if we had sensor data that are coming in, it will be going to that spout, right? So it will be taking that and streaming it. And then there's bolts. Think of them as workers. So a spout can be fed into multiple bolts, and it can do filters, aggregation, joins, and DB read and write. So what happens is that you have data coming in, and these workers can do different things to them. So you can add a bunch of numbers, or you can write them to a database. So this is how Twitter works. So it might want to find out, how many people are tweeting about a specific topic in real time. And then it could also say, okay, I want to store all this data, right? So there are multiple things you can do using different workers. So, I went backwards. So here's how it works. You have a little source that's coming in, and you have workers that pick work out of them. So you can stream them together into a network, essentially. And here's something that works with Storm. The way it works is that it allows you to do streaming in real time. It's developed by LinkedIn. So it works in a combination of Storm, right? So here's something interesting, is that you can send almost, I would say 200,000 messages if you wanted to per second to a machine, just like one machine, to a cluster that has just one machine. So if you have multiple machines, you can handle millions of messages using this combination, meaning that I can run hundreds of thousands of sensors that sends data into the system using the message protocol. So the way it would work is that you implement a Kafka client. So essentially it's a messaging protocol. Messaging is pretty simple. You do a send and then you do just a receive. And then you can use Storm as a base for it to be able to scale. So we actually have samples that you can run yourself that takes in GPS data and plot them on a map. And you can also store them into a database and do all kinds of interesting things with it. So this would be a very interesting project for people who want to do data ingestion and want to do some real-time data processing. So here's a very simple example. All this is doing is that I built a Kafka Storm combination, and then as the data is coming in, so you can see there's a little download link for the client. So I can send probably 4,000 or 5,000 messages easily to it using one client, and then I can scale it out to many, many different clients, hitting it from different machines, and it can handle up to 100,000 messages in this particular instance. So if you have lots and lots of data that are coming in and you want to do real-time processing, do the aggregation first, then store them in a database. This is a really good piece of software to be able to use. So here are the possible applications. One is that when you have a sensor network, you really want to keep these machines running. You don't really want them to go down, right? Otherwise, the data is just permanently lost. That's why cloud computing works so well here, is because we have much better network than anyone else that's out there. And the Internet of Things, so machines don't sleep. I know some people don't sleep, but machines definitely don't sleep. So it could be sending your messages anytime. So we really can't afford that downtime to be able to do things. And then also, I could have 100 sensors today, but tomorrow I could have 10,000. And all I really have to do is to go on the backend cloud and move the slider and say I want 10 more machines to handle the workload. It scales linearly because you have certain amount of workers that are allocated for processing. So if you move the slider, the number of workers just go up to do the same data ingestion. Smart buildings and smart city, this is actually a great application for this. So we have a Microsoft project called the 88 Acres. You can go online and find it. 88, just 8 acres, ACRES. So what this project does is it monitors everything that happens on Microsoft campus. So we know exactly how much electricity we're using at a specific time. We also know which building has a bad air conditioning. So everything is wired. So you don't have to have someone. So it used to be that we send a lot of these maintenance workers to go to each building and check everything. So it takes about 5 weeks for someone to go through the entire campus. So now it's 2 minutes. Essentially, you can get an overview of exactly what's happening on Microsoft campus in 2 minutes or so. So here's like a diagram of what's happening. So right now, at that particular moment, Microsoft is using 64 megawatts. And that's actually a lot of power if you think about it. So we have, I don't know, 100 buildings over on Seattle campus. We have 40,000 people in Seattle. So it uses a lot of power. I mean, we definitely do. So for example, if we just happen to use a bit more power, the Seattle grid would actually feel it. So you got to be really careful not to have those spikes actually happen. So if you look at this diagram, so this is the power consumption during each day. So you can pretty much figure out that people go to work here at 5 a.m. or 6 a.m. So somebody can start going to work at 6 a.m. So by the time it's probably 9 a.m., it really goes up quite a bit, actually 10 a.m. or something. And then you see this little dip here? Take a guess what that is. People going to lunch. So when people go to lunch, they're not on their computers. You can see that there's a little dip of energy consumption, just a little bit. And then the lights are on, it's just computers start working for a little while. And then in the evenings, it just goes down. And at night, you can see that there's a little spike around that time. So these are probably air conditionings or other things that started turning on or maintenance work that happens. So you can really see how these things work in real time. And you can open any building and take a look at what's happening at that time. So how many people there are in there, because it's hooked up with the badge system, and how much power is being consumed. And we can navigate through this map and click on any of the buildings. So all these red dots are saying there's a problem. So there could be mice stuck in the ventilation or something happens. There's a little red dot there. And then you can draw in and say, hey, what are the problems that we're having? And this particular building, and what are the problems? So this is the Xbox lab, and it shows you how much power is being used, and what are the vents doing. And you can look at the building and find out in which location we're having problems. So for example, right now we have a fault. It's a level 5, which means it doesn't really matter. It's a small problem, we don't care. It's going to cost us about $169 if we don't fix it. So it's no problem. If it's a big problem, for example, my office is on fire, then they'll probably come fix it, right? What's interesting here is that there's 2 million data points being ingested. There are 2 million data points being sent to these servers. This is actually using SQL Server and other things. So let's just say if we really start going crazy, we have the entire city of Beijing. Each building is wired to a sensor. How would you be able to do that? So one possibility is that you would use that Storm Kafka combination that I showed you, right? So being able to really scale out linearly as there's more data coming in. And it works great in our cloud because we provide the underlying hardware service, hardware and software service that ensures that it's always running. So we have a training class that happens tomorrow and Thursday. So if you're not signed up, that's okay. I have a link on this deck. Just get your cameras ready and you can take a picture of it. And it will have a link to it. And so, not here yet. So let me explain what I teach in this particular class. And eventually we might bring it online. I would really want and welcome you guys to take that class online if possible in the near future. And in the meantime, you can study that on your own. So in day one, we have an introduction to Windows Azure, and then we have an Azure Websites Lab. So websites allows you to create a website, and you can create a blog, you can create anything you want, ASP.NET, PHP, anything you can think of that's a web application, very easily. There's 10 websites that's free. And then you can also create these Azure virtual machines. So virtual machines are essentially a workstation in the cloud or a VM, just like how your servers work, right? You just have a machine that's sitting in the cloud. It will save everything you do. It's a hard drive that's remote. So it's sitting in the Blob Storage. So as you're reading and writing, that data is kept 3 copies, meaning that your hard drives, you have 3 hard drives sitting in the cloud. So one of them dies, that's okay. So it gives you the reliability of that. So that's virtual machines. You can have Linux and Windows on it. And then there's Windows Azure Storage. So this is a remote storage system that we built, which allows you to be able to take advantage of stateless applications, meaning that you should probably not write things to your local hard drive if you want to keep it scalable. So you will copy them to the Blob Storage. And also, for the cloud services, we have a little lab that shows you how to do communication between multiple computers, or between multiple machines. And then finally, that concludes day one, and then we go to day 2. So day 2 is mostly about compute at scale. So we have some HPC labs, and the HPC lab shows you how to use MATLAB, a cluster, use multiple machines to run MATLAB samples. And we also have a Linux cluster lab. It shows you how to build, just type in a command and create a cluster that consists of multiple Linux machines. And then we also have Excel and data visualization in the afternoon. We'll show you how to run Hadoop and other type of NoSQL database systems. So it allows you to process your data in parallel, right? And then there's the streaming data. This is what I discussed already, which is Kafka and Storm, right? So you'll be able to ingest data and then do the real-time processing and also store the data in a scalable fashion. So that's the training materials. And then, get your cameras ready. This is the URL. If you want the training material, it's about 140 megabytes. So it's and it's also going to change. So what I will do is I will update that URL when it changes. So you can still keep that link. So that link will always work. Okay, so let me go to the end. So we also have a Windows Azure for Research program. So each of you have one of these little pamphlets, so take them home if you like to. So there's a URL on them that says Azure for Research. So you go to that URL. It shows you when we actually do training. I think there's going to be 7 trainings in China at some point. It's completely free. You just have to sign up for it. And the other thing is that we have LinkedIn URLs. So can you actually access LinkedIn in China? Does anybody know? Okay, then you can. I think you probably can. I think Twitter you cannot access, but I think you can do that in the cloud. But that would actually make it happen. So the program, we're awarding a significant amount of Windows Azure hours for researchers. So you have a really good project, please do apply. And we really want to see some innovative uses of cloud computing. So using Windows Azure in ways that other people haven't really used. So we'd like to see projects that are always on, have been running for a long time. We'd like to see you do science that you weren't able to do with the resources that you just had on premise or your laptop, right? So please do take a look at this, and there's a URL which you can submit proposal. There's Dennis. So Dennis runs the program for Azure for Research, and you can, if you have questions, you can ask the gentleman in the back. There's Dennis. He's waving at you. I think that's all I have. Are there any questions? And don't be shy, and you can ask in Chinese. I'll translate even. Yeah. Any questions? No? Okay. Great. Thanks everyone for coming to the session.